Good morning, students. Let us start the class now. In the last class, we were discussing about the voltage divider bias, its approximate analysis as well as accurate analysis, and we had worked out one exercise as well. So, in today's class, we will work out slightly a different type of exercise. You can see on the screen there is a circuit diagram of the voltage divider bias, and this R1 is not given, VCC is not given, whereas VC is given. That means the voltage at the collector with respect to ground, that is given, and the base current 20 microampere is given, beta is given. So the question asked here is find values of VCC and R1 for the given circuit. Now just think about how do we proceed in solving this particular exercise. IB is given, beta is given, so you can easily find out IC. Once you find out IC, at the collector 10.6 volts is given with respect to ground. So you can easily find out the drop across this RC by using the value of IC. Now when you find the drop across RC, now the drop across RC plus this 10.6 volts is nothing but VCC, because the voltage at the collector with respect to ground is given, supply voltage is not given, in between there is only this series resistor, collector resistor. So when we find out the value of the collector current, we can find out the voltage drop across this collector resistor, and we can find out the value of VCC. Now, when we know this 10.6 volts, we can easily find out the voltage across this RE as well, 1.2 kilo ohms as well, when we know this IC. When we know IC, we can approximate IC with IE, and we can find out the voltage VE at the emitter. Once we find the voltage VE at the emitter, we can easily find out the voltage at the base. That is nothing but 0.7 plus VE. Now, when we know the voltage at the base, we can find out the current through this R2, because that is nothing but VB divided by 8.2 kilo ohms. Now, once we find out the current through this R2, add that current along with the base current, you will find out the current through R1. Now, when you already know VCC, when you already know this current, you can easily find out R1 there. Or you already know the base voltage, you know this VCC, you know the current. The difference between these two voltages you know, and the current going through R1 you know. So easily you can find out the value of R1. So this is how you have to analyze any particular given exercise. Initially you have to think a little about what all is given and how what all can be arrived by the given data. So gradually, if you keep on solving one by one, you will arrive at all the unknown quantities or unknown values. So this is the outline which I have given to you. Let me proceed with the solution of this problem now. The way in which I have discussed now, in the same way, the problem is being solved by me. So, given IB, we will find out IC 20 microampere into 100 is 2 milliampere. Now, when we obtain IC, we will find out VCC. You can just see is 2.7 kilo ohms into 2 milliampere plus the collector voltage 10.6 volts. So, we get the VCC as 16 volts. Now, when we get VCC as 16 volts, we can find out VE. We can find out VB as well. We can directly find out VB. VE is 2 into 1.2. 2 milliampere is the current and 1.2 kilo ohms is the value of RE. So VE is 2 into 1.2 plus 0.7. That is nothing but VB 3.1 volts. Now when we find out VB 3.1 volts, we can find out IR2. The current across R2 is 3.1 divided by 8.2 kilo ohms, that is 0.38 milliampere. Now we can add this 0.38 milliampere plus 0.02 milliampere. 20 microampere is nothing but 0.02 milliampere. So this current and the current across R2 is going to be the current through R1. So IR1 is 0.38 plus 0.02 is 0.4 milliampere. Now you know the current going through R1, and you know VCC, you know VB. So R1 is nothing but VCC minus VB divided by IR1. So that is 16 volts minus 3.1. 16 is VCC, 3.1 is VBB, or we can call it as VB also here in this case. So 16 minus 3.1 divided by the current through R1 is 0.4 milliampere. So we get the value of R1 as 32.25 kilo ohms. The nearest standard value is actually 33 kilo ohms. But as I have already told you, you need not remember all the standard values as such now. You can write the answer as you obtain here. Now this is an exercise of the voltage divider bias. So till now in our class we have discussed three biasing circuits. One is fixed bias and one is self bias, and the last one is voltage divider bias. Fixed bias is also called as base bias, and self bias is also called as emitter bias. Now please recall all the circuitry. You visualize all the circuitry. In all these circuits, always the input at the base and output as the collector. So we are always measuring the input as well as output with respect to ground, and in general emitter is common to base and collector. Out of the three terminals in a transistor or BJT, till now we have been discussing the circuits where at the base we give input, at the collector we take output, and that is when we bias the circuitry so that we will have a Q point which is VCC by 2 and at IC set by 2 ideally, and emitter is common. So this is called as common emitter configuration. Please recall whatever you have studied in basic electronics in the first year. Till now whatever we have discussed is common emitter configuration. And in the common emitter configuration, output current is larger than the input current, because output current is collector, input current is base. So there is a current amplification factor within the transistor called beta. And this beta is because of the difference between the area of collector and base. Please recall the construction of the transistor. Many times in the textbook they write all the three regions with equal area, but actually it is not so. Base will be smaller, collector will be bigger, even emitter will be bigger than the base. And emitter will be heavily doped because it has to emit electrons, and collector will be medium doped. So in such a case, as the charge carriers in the collector region are much larger in number when compared to the number of charge carriers at the base, there is already a current amplification factor within the transistor. That is because of the construction of the transistor itself. Now because of this, at the input the current is lesser and at the output current is larger. This is with respect to common emitter configuration. One more thing with respect to the common emitter configuration is that when the input current is rising or when the input voltage is rising, output current will be falling or the output voltage will be falling. This I had discussed earlier, which means when the input voltage is rising at the base, output voltage at the collector will be falling because the transistor will be switching on towards saturation region. So because of this particular switching activity, we also note one more point as far as the common emitter configuration is concerned. That is that output and input will have 180-degree phase shift. Means if you give a sine wave with the positive cycle and negative cycle at the input, at the output you will get the negative cycle and the positive cycle, which means there is a 180-degree phase shift between output and input. So to summarize, we have been discussing common emitter configuration, And in the common emitter configuration, output current is larger than the input current and the output voltage is 180 degree out of phase with the input voltage. These are the 2 points, and there are many other subtle points. All these other subtle points such as impedance and gain that we will discuss later on in this module itself when we perform AC analysis. Till now on the circuitry we have been doing only DC analysis. Later on we are going to perform AC analysis as well. Okay, so these two major points you have to remember. In the common emitter configuration, output current is larger than the input current. That means there is a current gain because of the beta itself. And the output waveform is 180 degree out of phase with the input waveform. That is because of the switching activity of the transistor itself. Now the third point what I want to mention is that we have told about current gain, but there is also voltage gain, right? When the input voltage is in millivolts, output voltage is in volts because of the switching activity of the power supply, switching activity of the transistor with the power supply. Again, remember all these points which I had discussed earlier. So now there is a current gain, there is a voltage gain, there is a 180 degree phase shift. When there is both current gain as well as voltage gain, we should come to a conclusion that this common emitter configuration also has a power gain. Power gain in the sense, there is a current gain because of beta, there is a voltage gain because of the power supply switching, and in totality, this common emitter configuration is going to produce power gain as well. So these three things you remember because later on I am going to discuss the other two configurations, common collector configuration and common base configuration. At the end, we are going to compare all these three configurations. So you will have to remember these 3 points. We will compare these configurations with these 3 points only. Current gain, voltage gain and current gain along with 180 degree phase shift, and finally power gain. Okay, if at all you have any questions, you can type it in the chat box. I'll keep watching the chat box. Otherwise, now let me proceed to the next configuration called common collector configuration. Look at this circuitry. Here, input is given at the base, output is taken at the emitter, and you can see a slightly different naming of the terminals with the author, but it is simply a different style. I am going to show you the equivalent circuit for this later on. The circuit is written in a different style, but it is the same as the earlier circuit. Here, he has connected one resistance at the emitter Re, and below which he has mentioned minus VEE. And he has shown the ground symbol at the collector. Now it simply means that negative terminal of the battery is connected at this point of Re and positive terminal of the battery is connected to the top side of the collector. And he has also shown Rb connected to ground. Now as collector is connected to ground, Rb is also connected to ground. It simply means that this Rb's other terminal is connected to the collector itself. That is why I told you this is a different style of writing circuitry. Otherwise, the circuit is the same. I will show you the equivalent circuitry. See, look at this circuit. This is the actual circuit which has been written in a different style with the author Boylestad. Now compare both these circuits. They are one and the same except for the capacitors. I have not included the capacitors here. I have just shown you the DC circuitry. Otherwise, the upper circuit and the lower circuit are one and the same. Let me explain. See, at the emitter there is this Re. R is other end is connected to negative terminal of the battery. That he is mentioning it as minus VEE. And Naturally, when the negative terminal of the battery is connected to the one end of the RE, the positive terminal of the battery should be connected to the collector, because ultimately the transistor has to switch on through this power supply. So the collector is connected to the positive, that itself he has shown it with the ground symbol. I have been telling you in the earlier classes that ground is only a reference point for us to measure the voltages. Otherwise, we need not always think that ground is 0 volts. That is what is evident here now. Ground need not be 0 volts. Ground is the point from which we measure. For example, with respect to the ground level, we are going to measure the height of any hill, or sometimes with the sea level, they say. They think that the sea level is the lowest level on the surface of earth, because water maintains its own level. So, above which we measure the height of all the mountains. And we say, Bengaluru city is these many feet up above sea level. And we also say Mount Everest is these many feet up above sea level. That sea level is the ground level. It does not mean that sea level is 0 level, because below sea level also there is again measurement of height even inside the ocean. The depth of the ocean also can be measured with the same reference. So it does not mean that the ground level is 0 level. It is only a reference for measurement. Same way, in our circuitry, whenever we put ground symbol, it does not mean that it is 0 volts. But in general, we keep on mentioning ground as 0 volts, because with respect to that, we measure all other voltages. So here, he has put ground symbol at the collector just because now with respect to collector, emitter is negative. With respect to collector, emitter is at the negative potential. So now you cannot say that the negative terminal of the battery is ground. Here the positive terminal of the battery is ground. Please understand this. This is an important point, because in the next semester you are going to study one course called linear integrated circuits. There you are going to study more about operational amplifier. Whenever you use operational amplifier, sometimes for some operational amplifier circuitry, we are going to use dual power supply. Dual power supply means we will be using plus VCC as well as minus VEE along with the ground. We will have plus 12 volts and minus 12 volts along with the ground. At that time, we say with respect to ground, one is at plus 12 volts, the other one is at minus 12 volts. So that is what is the basic understanding of the power supplies. Now, at the collector, he has put a ground symbol. I have discussed about the same. Now he has connected this RB to ground. Because he has put collector at ground symbol, it simply means that RB is connected to collector itself. Now you compare the upper circuit and lower circuit, they are one and the same. Base current is coming from this positive power supply only through RB. But the output is now not taken at the collector, output is taken at the emitter now. Because the output is taken at the emitter now, what happens is base is at the input, emitter is at the output. Naturally, the third term left out is collector. So we call this as common collector configuration. The same circuit will be later on called as emitter follower. Why is it called as emitter follower? We will see that when we perform the AC analysis. So now, from the power supply, current is coming to the base. From the base, it is going into VBE, and the base to emitter junction is forward biased, and the transistor will turn on. When the transistor turns on, at the emitter, the voltage is taken out as output. Again, one student, Sagar, is saying that screen is black, but I have shared the screen. Other students, please let me know whether it is visible. If the screen is black there, again refresh your screen. Yeah, it is visible. Bhargav is telling it is visible. So whenever you find such issues, again refresh or reload the page, you will see the screen, because here I am sharing the screen. Anyway, let me continue. Now when IB flows through RB, the transistor switches on and the voltage is across RE. So now we say we can bias this particular circuitry in such a way that here also we can follow the same requirements, that the Q point is half of VEE. We are calling this now as VEE because collector is common now. Because collector is common, at this particular circuitry he is calling it as VEE and he is giving the symbol minus VEE, which means emitter is connected to negative terminal. The flow of current is the same now. Flow of current will always be from collector to emitter. It will never change. That is why this transistor has a arrow mark symbol at the emitter. Just look at the symbol. Many times symbols talk a lot about the particular device. Now the symbol itself indicates that there is a base to collector junction. The line is joined here. Again, there is a base to emitter junction as the line is joined here. And between base and emitter, the arrow mark is there, which indicates the emitter current is going out of the emitter, which simply means that electrons are moving from the emitter to the collector. In general, we say the electric current is the flow of positive charge carriers. But in essence, there are only electrons. So in such a case, when electrons move to one direction, the current moves in the other direction. That is what we say. We always measure current as the flow of charge carriers from positive terminal to negative terminal. But in essence, it is the electrons moving from the negative terminal to the positive terminal, because it is the cathode which is going to release the electrons. And it is the emitter which is going to emit the electrons. Collector is the one which is going to collect the electrons. So the movement of electrons is in the other direction, whereas we measure current in the opposite direction. As we measure current in the opposite direction, this arrow mark indicates that the emitter current is flowing out of the emitter. Okay, that is why he is giving the power supply symbol here as minus VEE, because it cannot be plus EEE. If it is plus VEE, base to emitter junction will get reverse biased and the transistor will never turn on. Okay. Now, this is similar to the base bias circuitry, except that the resistor at the collector is shifted to the emitter. Otherwise, this is similar to the base bias circuitry. Just recall the base bias circuitry or the fixed bias circuitry. That circuit and this circuit are one and the same, except that the resistor at the collector is shifted to the the emitter. The reason is we cannot ground the emitter here. Why we cannot ground the emitter? We want to take the output at the emitter itself. That's why we cannot ground the emitter. We need one RE. Now, why we don't need a resistor at the collector? Because anyhow this RE is there. The resistor at the collector can be shifted to the resistor at the emitter, and even if a transistor completely goes into saturation, still this RE will be there across this power supply. So that way, essentially we don't require RC as such here. If we want, we can again include RC, and if we want, again we can convert the circuitry into voltage divider bias also. But that is not necessary as such, because we will not be using the other two configurations regularly in our designs. We will be using only the common emitter configuration to the maximum extent in all our digital as well as analog circuitry. The reason is that particular configuration is going to give the power gain. The other two configurations such as common collector and common base are not going to provide that much of power gain. That is the basic reason. You will understand the differences between these three configurations only when we complete the AC analysis. You will have to wait until then. But right now, simply understand, we are discussing this common collector configuration with the base bias circuitry itself. We don't have to go for again other two biasing circuitry such as self bias and voltage divider bias. We need not, because it is not going to give us any better results. Still, why do we discuss these two configurations then? The reason is, if we don't discuss all the three configurations, then we will not be able to understand which one is better out of all the three. So we will have to compare among all the three. That is the reason we discuss the other configurations. Fine. Now I hope you have understood that the circuitry which I have shown at the bottom is the same as the circuitry which is at the top, except for the two capacitors. C1 is the blocking capacitor and C2 is the coupling capacitor. Except for these two capacitors which are required for supplying AC input and taking AC output. Otherwise, the circuitry is same. In fact, I put this circuitry at the lower side so as to clarify that we can write circuits in many different styles. That's all, using different symbols. Now this is common collector configuration. Let me elaborate this term once again. When AC comes at the base and AC is coming out of the emitter, now input it as the base, output as the emitter. Now what happens to the collector? At the collector, again you visualize AC coming all the way, it is going all the way to collector, and collector is directly connected to the battery power supply. You again recall the term called AC ground. Now as far as the input AC signal is concerned, collector is at ground, because all the AC that comes to the collector gets absorbed by the power supply. That is why there is a ground symbol put here. That is the reason why the author Boylestad puts this ground symbol here. Again he puts the same ground symbol at the other end of RB itself, which simply indicates that RB is connected to collector only. Wherever ground symbol is put, you should always visualize that they are all connected together. Just like the sea level. Wherever the sea level is mentioned, it is the same all over the earth, all over the globe, whether it is India or USA or Japan or China or anywhere, England, anywhere, South Africa, Australia, anywhere. Wherever the sea level is the same. So, if they simply put a symbol as a sea level, it is simply indicated that they are all one and the same and they are all connected together. Same way in the electronic circuits, whenever you see this ground symbol and whenever you see the VCC symbol anywhere, simply the plus symbol, you have to visualize that they are all connected together. That is the idea of putting symbols. In fact, just like doctors, they don't write the name of the medicine very clearly. The name of the medicine is understood only by the pharmacist. It is many times it is a symbolic representation. Same way, we engineers also, we use many symbols in our circuitry, only we will understand and others will not understand. For example, in mathematics, teachers and students keep using so many symbols. Those symbols, only those people who are using those symbols will understand, others will not understand. Same way, why we use symbols means we can write the circuitry in a compact fashion in a smaller area. We can optimize the writing of the circuit diagram and it will look neater. If you compare the upper diagram along with the lower diagram contains more details, whereas the upper diagram is neater or optimized because we are using symbols. That is the primary purpose of using these symbols. Now let me proceed with the DC analysis of this circuitry. Let us apply Kirchhoff's voltage law at the input side. At the input side, we can simply apply the KVL here. With reference to the lower circuitry, you just visualize. Now, VEE is applied across RB and VBE and RE. So we can write the expression straight away that it is IBRB plus VBE plus IERE equals VEE. The total voltage which is applied is across RB, across VBE and across RE. So we can simply write a expression VEE minus IBRB minus VBE minus IERE equals 0. Total voltage is VEE. There is a voltage drop across the RB, voltage drop across the base to emitter junction, voltage drop across the RE. We can straight away write VEE equals minus IBRB minus VBE minus IR equals 0. Now you already know that IE is nothing but 1 plus beta into IB. Substituting the value for IE as 1 plus beta into IB, we can straight away write an expression for IB. That is, IB equals VEE minus VBE divided by RB plus 1 plus beta into RE. Now, remember this expression is same as that expression we had obtained for self-bias as well. Okay. Now, this is IB. Once you know beta, you can easily find out IE also, IC also. Now, this is at the input side. Let us see at the output side. At the output side, again we can apply that Kirchhoff's voltage law. VEE is applied across collector, then it is VCE plus IERE equals VEE. At the output side, there is a voltage drop across collector and emitter, and then there is a drop across RE. So, VCE plus IERE equals VEE. Or else we can write it VCE equals VEE minus IERE. The voltage drop across collector and emitter is nothing but total supply voltage VEE minus the drop across the RE. So, VCE equals VEE minus IERE. And I hope you have understood this. This is a simple analysis. If you have understood all our earlier examples, this is basically a simpler example. Now, based on this, let us solve one exercise. There is an exercise, find the Q point for the given CC configuration, common collector configuration, and it's the same circuitry here now. You will have to visualize the power supply or a battery here with the positive terminal at the top and negative terminal at the bottom. You have to visualize that way. The value of RB is given, the value of RE is given, and we have to find out the Q point. Q point is nothing but the current flowing through the transistor and the voltage drop across the collector to emitter. If the configuration changes, the coordinates of the Q point will not change. Please remember that. We define the quiescent point or Q point as the point at which the transistor is half on and half off. It is exactly at the middle of the active region. So, we are taking output at the emitter now. It does not mean that now the Q point coordinates will change, because again it is between collector and emitter only. The transistor is switching between collector and emitter only. Just visualize that push button switch which I had told you earlier. Either a laptop key or a computer key, when you press, or even the mouse key, it is like a push button switch. When you press that, you can press it fully or you can press it half. When you press it fully, switch is fully on. When you press it half, switch can be kept at half position. Generally we don't do that. But it is possible. If when you don't press it, switch is fully off. Same way, you can visualize this transistor. At the base, it is the push button. And at the lower level, there are two terminals which can be connected together. Same case, when you press the push button on your laptop or on your desktop in the keyboard, or even in the mouse when you press that click, what happens there is two terminals of the wire are connected together, and that is when the electric current flows. It is basically a switch there. Same way you visualize. If you visualize that way, when the transistor switches on half, there is a half current flowing. Half current is that IC sat by 2. And there is a voltage drop. Ideally, it should be the supply voltage divided by 2. So the coordinates of the Q point will remain the same. Now let us try to solve this exercise. We can ignore this C1 and C2 for the time being because right now we are doing only DC analysis. But these capacitors become important when we start performing AC analysis in the future classes. So now let me solve this problem. IB, direct substitution, is VEE minus VBE divided by RB plus 1 plus beta into RE. You are already familiar with this particular equation. So 20 minus 0.7 divided by 240k plus 91 into 2k. Beta given is 90. So it is 1 plus beta 91 into 2k is RE. So we get the value of IB as 45.73 microamperes. When we know IB, we will simply use the other expression for finding out VCE. Now, we can find out IEQ, quiescent point current at the emitter, is nothing but 1 plus beta into IB, that is nothing but 4.16 milliamperes. When you find out 4.16 milliampere, you can easily find out VECQ. I am writing it as VECQ, emitter to collector. I am writing it this way because collector is ground. According to this configuration, collector is common to base and emitter, so collector is ground. So instead of ICQ, I have written IEQ. Instead of VCEQ, I have written VECQ. But the coordinates of the Q point are the same. It is the voltage drop across the transistor and the current through the transistor. It is the same. Only thing is the way in which we use notations will become different because the common terminal here is now collector. So VECQ is 20 minus 4.16 into 2. Total voltage is 20 volts minus the drop across this RE is 4.16 milliampere into 2K. So the VECQ is 11.68 volts. Now you can conclude supply voltage is 20 volts whereas the Q point is at around 12 volts. So we can immediately say that the transistor is now in the active region itself. It is not exactly in the middle of the active region. If it has to be in the middle of the active region, then VEC should be ideally 10 volts. It is not so in this case, but still the transistor is in the active region. Safely we can say that. So this is the common collector configuration. Next I am moving on to the common base configuration. And all these three configurations AC analysis we are going to perform in the future classes just to compare all the three. Otherwise, we don't have to go into more detail about this common collector configuration as I told you earlier. We need not have again voltage divider bias in common collector, or we need not have self bias in common collector because it is not going to give you lot of advantages for us. That anyhow we are going to discuss again in the future classes. Let me move on to the common base configuration now. Look at this circuitry. Now here, between base and emitter, there is one power supply called VEE. And between base and collector, there is another power supply called VCC. And base is connected to ground. Again, I am telling you, ground is not 0 volts. You can see here, positive terminal of VEE is connected to the negative terminal of VCC. And we are using this point for our measurement as a reference point. So it need not be always 0 volts. It is our reference. Now when we take it as a reference, you may think that, sir, base is connected to ground. Will the transistor switch on? You may think that way. Answer is, transistor will switch on because ground is not 0 volts. That is why I have been telling you again and again, don't think that ground is 0 volts. If ground is 0 volts, transistor will not turn on at all. We simply put a symbol here just to indicate that it is the reference point for our measurement. I keep on repeating this again and again so that you will remember this again and again. Understanding is something else, and after understanding, remembering it is something else. These concepts you will have to remember for the lifelong. As long as you remain as an electronics engineer, you will have to remember these basic concepts lifelong. That is why I keep on repeating these statements. Now, the transistor will switch on if the base to emitter junction is forward biased. See, VEE positive terminal is connected to the base and emitter is connected through RE to the negative terminal of this VEE. So at the input side, there is a loop there. Through this loop, we can simply write that VEE equals VBE plus IERE. The total power supply across this input loop is nothing but the drop across base to emitter and the drop across the RE. We can simply write the equation here. So that indicates that the transistor is switching on through this VEE. Now you may think that because there is VCC here, negative terminal is there, transistor may switch off. No. Why? If the transistor has to switch on, base to emitter junction must be forward biased. Base to emitter junction is forward biased by means of this VEE itself. So at the input side, the base to emitter junction is forward biased. Now what happens at the output side? At the output side, again we can write an equation that total voltage applied across this loop is VCC, and we can say that VCC equals ICRC plus VCB. If you go in this direction, we should say that it is ICRC plus VCB because we are going from collector to base. So we can apply a KVL to the input loop, we can apply a KVL to the output loop, and we can find out the remaining unknown quantities, and we can find out the Q point. Now you may wonder, in our earlier two configurations we had one power supply. Now in this configuration, why we need two power supplies? Yes, we need two power supplies because we should ensure that the base to emitter junction is forward biased. At the same time, we should also ensure that collector is also given a power supply. That is why, as there are two distinct loops here, and as base is common to input and output, here the input is emitter and output is collector. Again, don't get confused here. You may think that emitter's arrow mark is toward the outside, and how can emitter be input? You may think that way. But emitter can be input for AC. It is not for DC. We are always applying AC signal at the input. Now a small change at the emitter will cause that change at the collector also, because the switching of the transistor is going to be affected. Always remember that this transistor is kept at half on. Now it can always turn into the either fully on or fully off state by the effect of the input signal which we apply, and that input signal is always AC. Now because of this, even emitter can be input. You should always think the amplifier circuit in terms of AC and not in terms of DC. Otherwise, if you keep thinking in terms of DC, immediately you will come to a conclusion that as the arrow mark at the emitter is toward the outside, how can current go inside the emitter? Current into the emitter will not go at all, because we have biased the circuitry in such a way that base to emitter junction is forward biased. So DC current is always going out of the emitter itself. That way the working of the emitter is not affected. But we keep the transistor in half on region. Later on we apply AC input. Then only the switching of the transistor is slightly affected towards saturation or towards cutoff. That is when we take the output at the collector. Now, if these basics are understood, again in the next class, I am going to discuss this circuit once again. In the next class only, we will derive the equations for the Q point. It's already time now, so I'll end the class now. I'll be putting the attendance link in the Google class. Please mark all your attendances.